Today we have a double-length colloquium talks. We arranged it around the acronym here, CEPC and SppC. So I'm extremely happy to introduce Dr. Yifang Wang, who's the director of IAMS Beijing. Dr. Wang received his under at Nanjing University in 1984. I mention this because he was then selected by Sam Ting to be part of the L3 team. It's a very special process, some of you may know. And with that, I think by Ting's style, he was assigned to Florence and received his PhD in 1991. So after a year as an INFN is the Italian funding agency for particle physics. He spent 1 year under INFN and then went to MIT from 92 to 96 as research staff. And after that, I think he showed admirable character. He left the Ting group and went to Stanford, of all places, right? And actually switched to neutrino physics. In early 2001, he returned to China, to IAMS, I think starting somewhat from ground up, but soon became the leader of the MES3 upgrade and also started organizing the IAMS experiment. So if I jump forward, 2012, the experiment had a big discovery of the third mixing angle of neutrino physics. So with that, I think within China, he received the 10,000 talent program. Now, if you know old scripture, talent here should be counted in weight of gold. So that's what 10,000 talent means, okay? And also for that, he received the 2014 Panofsky Prize with a co-spokesperson, Camille Luke, who's also in Taiwan right now, who's at Berkeley. This year's worthy of special mention, not just because of the program he's pushing, but he received, not just him, I think 5 neutrino experiments received the Fundamental Physics Breakthrough Prize. So he's one of the recipients, if you want. But I think, I would say making me most happy, but the most unusual thing is that yesterday there was the public announcement that he's been elected to the Chinese Academy. So we're extremely glad that the second day, we're so lucky to have Director Wang. Okay, Yifang, the floor is yours.
So thanks very much for the invitation. It's my great pleasure to come here to talk about physics. I've been visiting Taipei and Kaohsiung, I don't know, 5, 6 more times, but never gave, say, talks in such a big audience, neither in academic Sinica, in National Taiwan University, or at any other places. So extremely glad to meet all of you and talk about physics. So it is, as George said, it's not certainly it's not a rank. So just by accident that I was 3 or 4 days ago, I was informed that I should go there and get certificate, and then the same day, just 1 hour after that, I went to airport to come to Taipei. So certainly it's a great pleasure to see all the old friends, a lot of people been visiting IAMS, and also paid a lot of attention to particle physics progress in China in the last probably many more years, but what I know is 10 or 15 years. Before that, there must be also more, but I don't know. So having all the good friends interested on the future of particle physics, I think it's really great. So my talk today is talking about CEPC-SppC. So CEPC stands for Circular Electron Positron Collider. You probably know that in Beijing we have another machine, it's the E+- collider called the BEPC. So the reason we choose CEPC is the next step of BEPC. And we believe that the trend starting from 30 years ago in China on the science and particle physics will be continued, and we hope we can come up with something that our next generation, the next generations can benefit from that. Particularly, we benefit a lot from DPC, but we cannot just sitting there and not thinking about future. So CPC is our thinking for the future. Of course, there are a lot of difficulties and issues, but we believe that if the goal is correct and if we do the right, it should happen and can happen. So today, let me talk about the let me start to talk about why we would like to measure the E plus minus collisions at Higgs peak. So you can see from these slides, you all know that the Higgs has been discovered in 2012. So of course everybody believe that all the existing particles predicted by standard model are all there. So easily you can ask whether the game is over and should we just leave the field and do something else. Of course, there are a lot of very famous particle physicists say that. They even say that 20 years ago, saying that particle physics is over and you guys should do condensed matter science, life science, and many other things, but not particle physics. So after 20 years, 30 years, the particle physics still moving forward successfully. So we don't believe that this is the end, and there must be a future. Another question is the LHC. So a lot of people think that we should wait for the results from LHC to build a new machine. So I will touch this point later on. And of course, there's the IRC. You know that the International Linear Collider, people have been working on that for at least 20 years. And we get nowhere. And we have no idea whether the Japanese government is going to put money into it for this project. and a lot of doubt that Japanese is really going to put money into the project. Of course, we assume that the IRC will happen, because otherwise you always assume other people doing something bad and we do the best. So this is not the right way. So we believe, or at least we assume IRC will go ahead. By that assumption, do we need a new machine? I think that's the question. So in the end, it is actually the question, where is the future of our field, particle physics? So if you look at the physics, we have a standard model. After Higgs discovery, a lot of people saying that it's over, it's complete. But in fact, we have many reasons that standard model is not final theory, final solution. We still have a lot of unknowns. It's not complete. There are a long list of questions. For example, from the neutrinos to top quark, mass differ by a factor of 10 to 13. There's no reason that we couldn't understand this easily. And the second problem is so-called the naturalist problem. If there's no new physics, starting from now, 100 GeV, all the way up to the Planck scale, then to get the right Higgs mass at the 120 GeV, you need to write down the formula like this. And this 120 GeV came from the sum or the subtraction of this formula, and you see that it had to be very, very precise at the last digit. Then you get 125 GeV. So this is weird, and I don't think everybody believes this is normal, natural, and will happen for sure like this. So we believe that there will be new physics, and this cutoff lambda is not Planck scale at this place. It should be at 1 to 2 TeV, and 1 to 10 TeV. If it's 10 TeV, then the cancellation is not the 10 to minus 34. It's 10 to the minus 2 to 10 to minus 4. So we believe there should be physics, new physics somewhere to make this cutoff down to a level that nowadays technologists can access or find something new at 1 to 10 TeV kind of level. Then you have this plot. You see that the top mass and the Higgs mass, this is experimental data, sitting in between the instability region and the stable region. So this is very strange. Huh? Like, it is in the so-called metastable range. Personally, I also don't understand why it is like this, and it is natural. So there must be deeper reasons for that. Of course, there are some superficial kind of questions like we have a lot of free parameters in standard model. Almost all of them are related to Higgs. We have no way to calculate or to determine the mass of all these elementary particles. So I think we need to understand or try to answer this question: what is the fundamental theories behind all of this, and to explain all of these issues in a natural way. There are also experimental evidence beyond standard model. If you look at the coupling constant of strong, weak, and electromagnetic interactions, they end up a place like this. So, which means that these two series will not be unified. If you put some so-called supersymmetric model, minimum supersymmetric model, they cross the same point. So at least this looks like very reasonable. But the problem is that we haven't found anything at LHC. So this is actually a big question mark, whether we are able to resolve this controversy or not. And also we all know that the universe is made of normal particles, and but from gravity you need to have a dark matter. So these kind of dark matter particles not exist in standard model. We should understand why, and we should try to find it. And in the standard model, we have CP, but the CP in the quark sector is not large enough to explain the matter-antimatter symmetry in the universe. So with the new CP kind of mechanism, large enough to expand the matter-antimatter symmetry. Of course, if AMS is successful, very, very lucky, they may find a natural antimatter, and then this explanation is not needed. But up to now, there's no evidence that there is any antimatter space or galaxy in the universe. We have another problem with neutrinos. Neutrino has a mass which is in contradiction with standard model. So we need to modify the standard model, but the problem is that now we don't know how to modify it. We need the new experimental results to tell us how to modify it. And it looks like CEPC can provide many of the explanations, like this issue, standard model, and so on. Dark matter particles can be explained by CEPC. So CEPC is a very nice theory. But the problem is that we haven't found anything new in the HC. The issue will be left to the next generation accelerators and also next generation people. After the Higgs discovery, there are new tasks. This new task can be listed. It's not a complete list, but you can easily ask whether this new Higgs is completely consistent with the standard model. Whether this Higgs is a composite or elementary. Because up to now, we only found spin zero particles which are composite. We never had any elementary particles which are spin zero. This is only one. And we never see point-like scalars. So, like, if there are any new type of Higgs, which is in the same family of the Higgs, this kind of new Higgs is predicted by the supersymmetric models. So there is a possibility there. And also new properties, CP violation, and so on. Indeed, there's a major issue here, is that up to now we only observe this Higgs which give you some kind of potential well like this. But indeed, from a point of view of field theory, this potential could be this red wave or this green wave. And the experimental data only find here. So we have to understand which one is correct. And this is extremely important for the evolution of the universe. And more phenomenological kind of issues is we have a number of new couplings we have to measure. They only concerned with the Higgs. All the other particles, they don't have kind of recover coupling constant with the cell. And also self-couplings, H3, H4. At HC you get 50%, and HC for HT tau tau HBBH TT couplings is roughly 10%. So this is not good enough. And this HC is after the 3,000 inverse picobar kind of high unit results. So it's not the current day's precision. Current day's precision is much worse than this. So to summarize what we asked for, I think we conclude that there should be no new physics, and also there's some so-called standard physics. All this measurement need to be done and need to learn. We have many machines in the past, B factories, C factories, phi factories, so on. We measure all these constants. Higgs is the most important particle and the less known elementary particle. So we should have a new machine to study very carefully up to a very great detail. RNC, we believe, is not enough, even if it's going to be built today. There are also a lot of issues which IRC running at 500 GeV is not going to complete our understanding of the whole picture of the universe. So we think that high energy frontier is still center of particle physics. So when LHC is over, the whole world will need a new machine, a proton machine, to study all the problems we just mentioned. So what can we do like this? So we proposed in the year of 2012 to build two machines. One is CEPC, I just explained to you, and this is a circular Higgs factory running at 250 GeV. You can produce the Higgs very high statistics. And then only this one machine we believe is not enough. So we should be able to put a proton collider, just like HC, in the same terminal. Once you get the terminal, you can move to a new machine. So this kind of natural continuation from BPC, BPC2, CPC, SppC is a long kind of journey towards the future. So we have this terminal, we have a first booster for electron and positrons, and now we have storage rings for electron-positron collision. Then after that, we have a big ring for the proton machine. The idea is to have a circumference between 550 kilometers to, say, 100 kilometers. We believe 100 is probably too large, but 50 is too small. It should be somewhere in between. Sorry, I have a coffee, so. So, the combination of these two machines will give you the following scientific benefit. The first is that electron-positron collider running at 90 GeV, 250 GeV, and possibly 350 GeV. So by having the machine running at 3 different energy points, you get the Higgs factory, which can give you 1 million Higgs particles in 5 to 10 years of running. So you can study all the details of the Higgs, and as I mentioned before, the mass, coupling, and so on. And also, it is complementary to IRC. I will come back to this point. And then we can look for hints for new physics. You can also do the Z and the W factory. You do a precision test of standard model.
and try to find the deviations. And then it will give you indication whether and how to move to the next step for the proton collider. In the face of a proton collider, you can do a direct search of new particles, which may already indicated by electron machine. You can also do the precision test of standard model, for example, Higgs triple cut constant, and so on. So these two machines is a combination of the precision measurement and new particle searches. They are very much complementary with each other. And this is, we believe, the ideal solution for the future. This is the design goal of CEPC and the CERN's FCCE. So this is a linear collider, the luminosity going up this way. And this is the circular machine, the luminosity going down this way. So at something like 500, 600 GeV, linear collider gain the advantages. But below that, circular collider give you very good advantage. Remember, we want to run at 250 GeV for Higgs factory, so we are somewhere here. We are at least many order of magnitude higher on luminosity compared to IFC. Of course, our CPC looks like lower than FCC, but remember that FCC, in the later on we'll talk about the designs. They use all the possible good things into this machine. So of course, you get best luminosity. But you have a lot of practical issues they basically did not address. So what we decided to work on this way, because we believe this kind of reasonable assumptions and they can be afforded. I mean, you have to give up somewhere, and you are not going to build a machine which is the best of everything. It's not realistic. For the SppC and the CCPP, currently the technology to band the proton machine is very much limited by the field strength of the dipole moment, which currently we can do 10 Tesla or 12 Tesla. And if you want to do 100 kilometer kind of machine, you need 20 Tesla. And from 10 or 12 to 20 Tesla, you need at least 20 years. So that's why we believe that building electron machine at first, and then doing the R&D for the magnet afterwards, and say 30 years later or 20 years later, we should be able to build this 100 TeV machine. From physics point of view, I understand that a lot of people think 100 TeV machine is more interesting. We should do it now. But even if I gave you $100 billion, you still cannot do it because you don't know how to do it. You have no way in 5 years being able to produce this kind of magnet, and there's even 16 Tesla can't do it. So CERN decided their baseline is not to build the electron machine. They would jump to the proton machine immediately. So they have this trouble, and their machine is designed to have 16 Tesla, not 20 Tesla. This is a waste of the turn, to my mind. So I think 20 Tesla or even higher is probably a better solution. If you want to do it quick, then you may get something, but you are going to waste the advantages of this turn. Of course, it's a big project, a lot of money involved. People will ask, you, are you sure you can find something new particles? Of course, I cannot guarantee. But if you look carefully and examine all the issues, we are not going to report for sure discovery of new particles. But we can tell you there are new physics, okay, for sure. And the new phenomena, and even though the new principles. So the pillars of this machine are threefold. One is the electron wave phase transition. This is self-coupling of the Higgs particles. We can look for dark matter, And I think the higher energy, the better. It's the only way you can do in the accelerator to see, to possibly see dark matters. And again, this naturally is a trouble to us. And even if you find out this is true, it's the new fundamental physics or new principles. So even you don't see anything new, that means nature is dead. And this is also a very important conclusion. So if we find anything, we didn't find anything new at the HC, the fine tuning is 10 to minus 2. It is possible. But if we don't find new physics at 100 TeV, this new machine, which means the fine tuning will end up 10 to minus 4. In the whole nature world, whatever science, physics, or even life science, anything which has so-called accidental cancellation at the level of 10 to minus 4 is never heard of. It's very hard to imagine this could happen. But if it happened, then of course we have a lot of other troubles ahead of us, and we should be able to try to solve this problem. And these are all fundamental issues or fundamental principles of physics, like whether we are in the universe or whether we are in the multiverse. It's fundamental issues to our physicists. People were asked whether we would like to wait for the results from HC to decide your machine. So if HC finds nothing, I think we have no choice. We have to go to high energy to see what's there and what's next. So an electron positron Higgs factory can give a first indication, and we go to 100 TeV afterwards. I think it's a very natural choice. If HC finds something new, of course it's a new era. It has to be beyond standard model, and HC cannot complete the whole spectrum for all the particles there. So you need a machine to complete the whole picture. If this is the case, of course, there is just justification for CERN to start proton machine immediately. So that's something you can look for. But I think the technology, even with 16 GeV, is not there. You still have to wait 10 or 20 years to start this machine. So no matter what, having an actual machine first, and for the next 20 years, and afterwards we build a proton machine in the same kernel, fits all this kind of possible scenarios. And any of these scenarios, I think CEPC plus SppC will work, and is the best solution to the future. People were asked, the so expensive things, China is still a poor country. Why you should do this? Why you want to do this? Why not just give the money to, I don't know, poor people to make them have a better life, or to put money into the space kind of industry, or whatever. I mean, you can imagine. But I think a machine like this is actually not affordable. It is affordable and not that expensive. So you look at the calculation here: BPC, SAC, LAP, HC, IRC, CPC-SppC. The total cost divided by the number of years they're going to construct this machine, and they divide by the GDP of that country. This is European, so it's not single country, but European Union. You can see that over many, many years, 30 or 40 years, the ratio is not very much different. The most aggressive kind of project is HC. It's 0.3 per meter. All the others is just 0.1 per meter. And if in the 80s or 90s, people are brave enough to imagine this kind of machines, I think now CPC and SppC is not going to be something awkward, impossible. I think it's possible. Just depend on the willingness of the